We are looking at now linear, homogeneous, non-homogeneous, differential equations. As a reminder, the non-homogeneous part is where you have something that is a proper term that only has the independent variable. Doesn't matter that your independent variable is x, like what I typed up here. And in fact, if you're using differential equations in any sort of physics-based field, you're probably not going to have x. And in fact, it's super duper really, I cannot stress it enough, rare to see x in those situations. It's almost always t for time. Okay. I do have a couple of examples prepped up in the future for this topic that transition over to t for time. Note, nothing's going to change other than your letter. Okay. The other thing to watch out for is the linear part of your differential equation, and that is simply saying that all of these coefficients in front of your dependent variable terms are only allowed to have your independent variables in them. Recall, that's the same definition we've had for linear since like day one. Okay? And I went ahead just for comparing and contrasting. We also are going to need to worry about our homogeneous differential equation, and the one that I actually typed up here would be the associated homogeneous differential equation. And why would I call this guy the associated version? Well, because this part right here that has all the dependent variable terms looks like it exactly matches the non-homogeneous expression up there. The only difference is now we took that term that used to have only independent variables and we made that term exactly 0. For non-homogeneous, you have to have that term, that's the independent variable term, cannot be 0. Okay? So that's the key distinction. Now, to remind yourself in terms of symbols, when we solve the homogeneous solution, like what we have in the past examples where we were only having homogeneous differential equations, that general solution of the homogeneous differential equation can be written as y with a lowercase h. The h is just indicating solution of homogeneous equation. Okay? Now, when we're dealing with the non-homogeneous equations, or the non-homogeneous differential equations, the new thing that we're going to need is we're going to need to actually find a particular solution. You could, if you had infinite time available to you, just go through and guess every possible function known to man until you found one that actually worked when you plugged it into your differential equation. Please do not really do that. Okay? So everything that we're going to do in this chapter 4, where we're focusing on the non-homogeneous differential equations, so that's really section 4.4 and on, is where we're going to have educated ways to get to, or ways to get an educated guess for, our particular solution. Okay? The general solution of the non-homogeneous differential equation is somebody that you can call y. Some books call it y with a G for general. But the main thing to know about this actual solution for your non-homogeneous differential equation is the fact that it has two parts. It's got the solution of the homogeneous, or the associated homogeneous differential equation, and then you have to add one of the particular solutions at the end. Okay? What that does is your particular solution will have no unknowns in it. It's an actual one specific function. There is no family of functions involved. And the homogeneous solution right there, that guy is going to be where your constants are involved. So for the overall general solution for the non-homogeneous differential equation, you will still have unknowns unless you have initial values, but all those unknowns will actually live inside of the homogeneous solution. Okay? So we've talked about some of that last time. I think I added in a couple new details, but let us also go over the method we're focusing in on today, or right now, which is our method of undetermined coefficients. So I'm going to jump through that example. So here is our method of undetermined coefficients. We are going ahead and assuming that we have constant coefficients for our differential equation, and you do have to have a non-homogeneous differential equation. Specifically, method of undetermined coefficients is only going to get you to the particular solution. So it's only half of the actual solution. You'll have to find the homogeneous solution doing the same method we would have if we had a homogeneous solution. So first thing that you would do in terms of finding this particular solution is you're going to guess a function that has the same format as your non-homogeneous part, and we have three main formats that we're allowed to have over there, and we talked about last time what were the formats of the guesses that corresponded to each of them, and I'll show that here in just a second. Then you take whatever you've guessed for your particular solution, you actually plug it into your differential equation, and all of the unknown coefficients that come up naturally in your guess, you'll then be able to solve for them. So the three types of functions that we're allowed to use for our non-homogeneous part of our differential equation is we're looking at polynomials, we're looking at exponential functions, and we're looking at trig functions that are either sines or cosines. And the key things that you've got to have here is, again, we just mentioned it, but you've got to have constant coefficients in front of your dependent variable terms, and your non-homogeneous part must correspond to one of those three function types-ish. We should get to the ish part at the end of today, and if not at the end of today, at the beginning of next time. So here are three types of functions. We've got polynomials. So what we said last time is you grab whatever your polynomial is that you're given for your non-homogeneous part of the differential equation. You go ahead and you figure out what degree that polynomial is, and then the guess for your particular solution is the general form, in other words, all of the terms of a polynomial of that exact same degree of the non-homogeneous part. So this example, your given non-homogeneous part is a polynomial of degree 4, which means our guess for that particular solution for that differential equation would have to be a degree 4 polynomial. We don't know what those coefficients are, which is why we've got the constants. It's the same idea of when we do our partial fractions, we know what the bottoms of the partial fractions are all going to equal. We don't necessarily know what the tops of the partial fractions are. We then have to go ahead and solve it. Okay. So then if you have an exponential form, you do have to have in the exponent simply a constant times x. You're not allowed to have other types of things in the top up there. So really it needs to be like a linear polynomial in the exponent. So here, what do? The general form of somebody that looks like that, it still looks like the exact same format, and then you've got a little coefficient in front. There is some things that can happen to this guy, and honestly, it can happen up here too. The only time that you would actually need to multiply by an additional copy of your independent variable is if this function for your guess actually matched one of your homogeneous solutions. And that happens most frequently with the exponential form, but this same trick right here does actually occur in any of these three cases. Now with a trig for one of your non-homogeneous part, maybe you have something like sine of 3x, or maybe you have f of x equals cosine of 3x. Turns out, regardless of whether you have the sine or the cosine for your non-homogeneous part, the guess is identically the same. It's this guy here with a sine term and a cosine term. So here, let me go ahead and put that comment we mentioned before. Note, if yp is a homogeneous solution, in other words, it is a solution of the associated homogeneous differential equation, what you have to do is do a new guess, and the new guess is the old guy times I can't write, just a second. The old guess times a copy of the independent variable. If that new guess is still one of the homogeneous solutions, you'd multiply by another copy of the independent variable. So that's what happens if your guess for your particular solution doesn't quite work out. Okay. So last time we ended on one example, specifically an example where we had a polynomial form. So today I wanted to go over examples of what happens if you have an exponential form, what happens if you have a trig form, and then depending on time, what happens if you get combinations of these guys for your non-homogeneous part. Any questions before we jump into examples, which is pretty much the rest of today? All right, I'm not seeing any questions come through, but if you come up with any, definitely send them my way. All right, so we did that one last time. So if we look at trying to find the particular solution of this differential equation, suppose you've got the differential equation that's listed there at the top, 3 times the second derivative of y plus the first derivative of y minus 2 times y, all equals 2 times cosine. Notice because this is not homogeneous, in other words, it's a non-homogeneous differential equation, and the part on the far side right here, this guy that is our f of x, does in fact have an x in it. That tells you your independent variable is x, and you don't have a choice of what you get to call your independent variable, like when we were back in our homogeneous situation. Okay? Now, I'm going to outline the structure that you would do if you wanted to go ahead and solve this differential equation for the general solution. However, we're not going to do all the steps because the only thing we want to do, according to that question directions, is find the particular solution. So normally what you would do is step 1, go ahead and look at the associated homogeneous differential equation. In other words, you cross off this 2 cosine x, replace it with a 0, use the characteristic equation on the resulting homogeneous differential equation, find the roots, find the functions associated with the roots, and put them all together. Okay? And then you'd have your solution for that associated homogeneous differential equation. I'm going to skip that step. So step 2 then, after you find your solution of your homogeneous differential equation, now is when we want to go ahead and find our particular solution. So step 1 for finding your particular solution is identifying what your function is, your non-homogeneous part of the differential equation. And we already did that. We already noted up at the top there, f of x equals 2 times cosine of x. So that means we can then go and look at our different cases that were on the previous slide and say, hey, we've got the situation where we have a trig function, which means we're going to grab the format associated with a trig function. Quick check. Our trig function has to be either sine or cosine. So yep, we have a cosine, not something like a tangent, so we can go ahead and use that format. And the format said you wanted to have some unknown coefficient, maybe a, times sine of something, plus unknown coefficient b times cosine of something. And if you want to reverse where those capital A's and B's are, you can. If you want to reverse where the sines and the cosines are, you can do that too. You can go ahead and flip-flop the order of all those things. But the thing you can't flip-flop and change up is what's inside the sine function and the cosine function. So here, if you're looking at what should go inside the sine or the cosine function, what should I plug into those 2 trig functions? Anybody got a guess? It should always match the same angle as is given in your non-homogeneous part. So here what's being plugged into our f of x function or plugged into the trig function associated, or that is our f of x function, is just an x. So we're just going to have an x plugged in both of those 2 slots. That's it. Now, second part of step 2 in finding our particular solution is now we need to actually figure out or find what those coefficients a and b are. Now, we did an example of this last time. Anybody remember what we should be doing to go ahead and solve for capital A and capital B? So it's a little bit of a process. We're going to want to take some derivatives, and we're going to take some derivatives because we want to plug this particular solution, or what we hope is the format for a particular solution, into the into the differential equation that we're actually given. So that whole guy up there at the top. So let's go ahead and do this in sequence. Where's a good place to put it? I'm going to go ahead and put our scratch work over here to the side. So I'm going to put the second derivative up top. So we'll do our work here bottom to top. We'll have our first derivative. On the bottom, we have the original guess. And our original guess here was a times sine plus b times cosine. Now, if you take the derivative of a sine plus b cosine, what should you get? Well, the sine part turns into who? Sine turns into, anybody got a guess? Yep, cosine. And the cosine after the b turns into who? It'll turn into negative sine. So I'm going to go ahead and flip the plus between the two terms to a subtraction between the two terms. Now we just have to do it again. So same thing applies. The cosine now after the a will turn into a negative sign, so we'll get negative a sine. I missed the I. Pretend there's an I there. And then we'll take the derivative of the sine after the b, and we'll get negative b cosine. Okay. Do a quick double check. Make sure I didn't screw up any of those derivatives. I always recommend that when you're plugging in things is you do a check to see if you haven't screwed up your derivatives. Why? Because that's the easiest place where mistakes happen in this whole process. All right, so let's go ahead and plug this stuff in. I'm going to go ahead and title what we're doing. That way we know what we're plugging in. So we've got 3 times the second derivative. Our second derivative of our guess for a particular solution is negative a sine minus b cosine. Then we add the first derivative, so that's a cosine minus b sine. And last term is subtract 2 times the original guess, so that's minus 2 times a sine plus b cosine. Not going to lie, trig functions have a tendency to feel the nastiest just because you get things like that where you're always going to have at least the 2 terms, so it's always a little bit bulky to deal with. So the question is in terms of, I'm guessing, typing this, where you can't put things into subscripts very well. How do you write this y to the second derivative with a p? Technically, that p for particular solution is in a subscript, but if you're typing it like in our chat, like you guys are, or if you're in an email, either of the 2 ways that you typed in, I'll know what you mean. But technically speaking, if you want to be super proper, it would be this. That underscore indicates put the thing after the underscore into the subscript. And then the parentheses indicate that the y subscript p is all one entity. And then after that, you'd have your second derivative symbol. Okay. But honestly, in terms of if you're just typing it up quickly to me, I will recognize either of the 2 cases. But with parentheses, there would be no misunderstanding. If you wrote that first way where the p is after the second derivative symbol, I might have a follow-up question with you saying, do you mean? Just to make sure that I'm reading what you're saying the same way you're thinking it. Okay. All right. So once we go ahead and plug in everything with the particular solutions guess, the next thing you want to do is actually figure out what the a and the b are. So here's where you combine like terms. Now, if you look at all of the terms we just wrote out, anybody have a guess on what we would consider like terms in this scenario? It would be based off the blank and the blank. Any guesses what you'd fill in those 2 blanks? So we group these guys based off of whether there was a sine or a cosine in the term. So I'm going to actually write it out, something times sine, and then we'll have something times cosine. I just sort of signpost it for us. So if we're looking for sine terms, well, we've got a sine term right here. So what would be the part that's being multiplied by sine in this first term? Hint, it's not negative a. So you'd have to multiply the 3 in. So you distribute the 3 in right here. So that guy being multiplied by sign is really negative 3a. Now, I don't have enough space on this slide to put that middle work, but if it will help, definitely, I cannot stress this enough, multiply any of these coefficients like the 3 up here, or in our last expression, the negative 2, actually distribute that constant all the way through. And you'd have a middle step that we don't have right here. Now, if we look at our next term with sign in it, it looks like it's in the second set of parentheses. So right here, we've got that negative b sign. There's no coefficient other than a 1 in front of the parentheses, so that's just going to be negative b. And the last sign is in the last set of parentheses. Again, it's not going to be just a. We'll multiply that negative 2 inside the parentheses and get negative 2a. And of course, all that stuff in the parentheses can be combined or collapsed down. The 2a terms can be added together, and you really get negative 5a minus b. Now we'll do the same thing with cosine, and that's all the pieces and parts from above that aren't underlined. So with the first cosine right here, we'll have the negative b. Don't forget to multiply it by 3. So we'll have here negative 3b. For our cosine in the second set of parentheses, we have a times cosine. There's no coefficient other than 1 outside of those set of parentheses, so we don't have to worry about multiplying the a by anything. And the last set of parentheses, our cosine right here, don't forget to multiply in or distribute the negative 2. So this guy would be a negative 2b. Now, anybody notice anything interesting about what your sine and your cosine are being multiplied by? Anybody see a pattern with those things inside the last parentheses? Yeah, the two expressions look almost exactly the same. There is only one change, and it's what you guys have pointed out. It's your a and your b have flip-flopped. That is pretty standard with trig functions. So if you see something where the pattern looks almost exactly the same, except the letters were swapped, don't worry about it. That's what should be happening. So what I'm going to do here is I'm going to go ahead and say, what are those coefficients with the expressions of a and b? What do they need to be set equal to? So this is where you go back and compare everything to your non-homogeneous part of your differential equation. So we just plugged our guess in to the actual differential equation. So what we just found, those expressions are supposed to be equal to the two cosines. Now remember, sines and cosines can't be added together. So what does this mean? This means that from sine, you know the following. You know that negative 5a minus b, wow, that's not going to be a b, it's negative b, minus b has to equal what? Any guesses? Yep, it would have to equal 0 because there is no sign in the actual f of x in the non-homogeneous part. Now, if you take the coefficient from cosine, that if you actually added it all together, like a couple of you had sent to me, you get your positive a minus 5b. I went ahead and just lined the a's and the b's up in the same order. What's that guy supposed to equal? Remember, this coefficient came from cosine. Oh, I've got tons of answers for this one. Yes, this one's supposed to be 2. So now we have two equations, two unknowns. That is something that you can totally solve for your capital A and your capital B. No worries. Now, are you guys okay if I just tell you what capital A and capital B equaled? Can I assume you're all okay with doing the algebra on your own? All right, I'm getting multiple responses. I'm going to assume that's okay. So capital A turned out to equal negative 5 over 13. And capital B turned out to equal 1 over 13. which means if we wanted the answer, this tells you that your particular solution of y should be, just plug in the a and the b to your guess. So here's your -5/13. And a was in front of sign. Always compare what the letters actually are in front of. So a is in front of sign, so we'll have sign. And then we have our b, our +1/13 times cosine. And assuming I did no typos in terms of solving for a and b previously to right now, that would be the particular solution, or the most efficient way to write your particular solution for this particular differential equation. And just for completeness, if we weren't solving just for the particular solution, but for the full solution of the differential equation, we would get, hey, grab the homogeneous solution that we would have already found in step 1 that we didn't find today, plus the particular solution that we just found. Okay? But I'm not doing this step 1 or step 2. Yes. So to answer the question, the 0 and the 2 came from our f of x. So let me put a little bit of a side note right here. Our f of x, the non-homogeneous part, can be written as 0 times sine plus 2 times cosine. So what we did is just compare the coefficients of what sine and cosine were supposed to equal. It's possible I flipped them. Just a second. Yep, I flipped them. So when I did this earlier, instead of saying a times cosine, I said a times, instead of saying a times sine, I said a times cosine. So you need to flip these two. Yeah, good call. And I was even just telling you, you need to be very careful about that. So this one here should actually be cosine, and that one should be sine. That's embarrassing. So no, you guys are totally right in doing that algebra to the side. Okay. Are there questions about this example? All right, well, that's the basics in terms of if you got a trig function. So if you have an exponential function for your non-homogeneous part, that's the only case we haven't looked at yet. So that is actually what our next example is. So for our next example, we want to, again, only looking at finding the particular solution of the differential equation, second derivative of y minus 4 times y equals 2 times e to the 3x. So again, if we signpost this, a step 1, which I'm going to go ahead and skip out on, we would go ahead and find the solution to the associated homogeneous differential equation. And remember, the associated homogeneous differential equation would be where you would simply cross off or get rid of that non-homogeneous part and replace it with a 0, solve the resulting homogeneous equation, whatever that answer is by way of your characteristic equation, roots, etc. That would be your answer for step 1. Now I'm going to get rid of the cross off, and whoa, just a second, wrong button. And then we're going to actually do step 2, which is find the particular solution. And just a second, I got to deal with something. I'll be right back. All right, sorry about that. I'm back. All right, so for step 2, if we wanted to find a guess for a particular solution, first thing you have to do is go ahead and figure out what your non-homogeneous part is. And then you say, all right, well, format for my non-homogeneous part is 2 times e to the 3x. So any guesses what format our particular solution should theoretically be in? Anybody have a guess? Yep, that is totally right. So let's write it in here. Got a little bit behind you guys. All right, so once you go ahead and have your guess, then you're ready to go ahead and plug it in. Well, I lie a little bit. You got to figure out what your derivatives are. So over to the side, let's go ahead and write down our derivatives. Now, something that I have found only after teaching this class is I used to write the derivatives of our particular solution from regular old function at the top and then first derivative, second derivative. And I would always, when I plugged it in, or more frequently than I would love to admit, plug them in the reverse order. What I have found is if you actually write it in this bottom to top way, you get a little bit more accuracy in terms of plugging in, or at least I do. So if we take our a times e to the 3x and we take its first derivative, what should we have? Don't overthink it. The a stays the same. What's the only thing that gets added? Yep. So you'll get an extra copy of 3 out front, so you have 3 times a times e to the 3x. Now what about the second derivative? What should the second derivative look like? I'll do the part that stays the same. Yep. So when you take the derivative again, you get another copy of 3, so you get a 9 times a times e to the 3x. Okay. So at this point, we're ready to go ahead and plug in. So we found our guess. Second thing, we go ahead and we plug in. So I'll go ahead and signpost us. We have second derivative of the particular solution minus 4 times the particular solution. So second derivative is 9a e to the 3x minus 4 times a to the 3x. So we go ahead and we say, all right, well, I feel like there should be more, especially after the last example, but there's not. Can you combine those terms together? It's always the thing to check. So like with our trig function, we couldn't combine everything together, but just the sine and the cosine terms. But here, yes, we are actually able to combine everything together. So you look and you say, hey, well, I definitely have an a in each of those terms. I definitely have the e to the 3x in each of those terms. So if you did actually add them together, what would be the number in front of the a? So you just be subtracting your 4 from your 9, and you'll get 5 times a times e to the 3x. And what is this thing supposed to equal if it's a solution? If the particular guess for the particular solution actually is a solution, I guess I should say. So we should have this whole thing equal to the non-homogeneous part. So it would be the 2 times the e to the 3x. So this part right here is what we're going to get, or what we're going to use to solve for a. So what do we have? This tells us that 5a has to be 2, or that a has to be what? Anybody got what? So we'll just move the 5 over. We'll get the 2 over 5 for our a. And last step is you go ahead and put it all together and get your actual answer. So this tells us that our particular solution is 2 over 5. Looking at the actual format we had before, so I don't make the silly mistake I did on the last example, we'll have 2 over 5 times e to the 3x, and that would be your particular solution. Notice, with your particular solution, there are no unknowns left. You solve for everything. Now, for completeness, if we were solving this differential equation completely, not just for the particular solution, the last step is to get the full solution for the entire differential equation. You take whatever we would have found for the homogeneous solution, and we add it to that particular solution we just found. Note, with the work we've done right now, we only have half the answer for the general solution of this entire non-homogeneous differential equation. I on purpose skipped out on step 1 just because I was trying to focus on the format for finding or guessing or getting your particular solution. Okay? Questions? Kind of making sense so far? Notice the procedure in terms of getting your particular solution after you have your guess is exactly the same, and getting that format of your guess you just look off of your three cases. Is it a polynomial form? Is it an exponential form? Is it a trig form? And you just match whatever format you have in your non-homogeneous part to that same format, except you change your coefficients out to arbitrary coefficients or those capital letters that you then have to solve for. So seeing no questions coming through, that's my tactic of stalling just a little bit to make sure you guys have 2e to the 3x, where, oh, here? That guy? Okay, so that came directly from your non-homogeneous part. So remember what we were trying to do? We were trying to plug into our equation. So what you can do is you can actually put it in a slightly different format. The structure here of sort of linking a bunch of equals together, that is a very, very formal math way of doing something. But you can do the slightly less precise, less formal way of the following. You can say, hey, second derivative minus 4 times the first derivative equals 2e to the 3x. Then you do your plug-in, so your 9a e to the 3x minus 4a e to the 3x equals your 2e to the 3x. So 5a e to the 3x equals, that was trying to be a 3, 2e to the 3x. And then you get down to the same spot of 5a equals 2, which still gets you to that same answer. Okay. So same idea. And if you would prefer to do it this other way, over to the side that I boxed, you're going to get fussed at in upper level math courses. But if you don't have to worry about upper level math courses, this is a perfectly fine way of just saying, hey, I need that first line. Let me plug in everything. Let me just do some algebra. Okay, so both ways perfectly fine. All right, seeing no other questions from you guys, I'm going to go on to another example. So the next example I have actually looks extraordinarily similar to the example we just finished working. So pay attention to what changes. Look right up here at this top where this differential equation part is. The directions are going to be exactly the same, so those words aren't going to change at all. This guy right here is going to change slightly. See if you can spot where it changed. Besides all the writing disappearing. Anybody spot what the change is? So it's super duper subtle. In fact, the first time you see it, if somebody doesn't point it out to you, you might miss it. That exponent on the e actually changes. So I'm going to try to work this problem two ways. Okay. So the first way is exactly what we've been doing for all of the other examples we've had today with dealing with particular solutions. The first thing is let's go ahead and find a guess for our particular solution. So our f of x, our non-homogeneous part, is that 2 times e to the x. So what do you guys think a good guess for a particular solution is? Don't overthink it. Oh, it's already up. So a times e to the 2x is totally a great guess for this particular solution. Once you've got your guess, we'll go ahead and compute all the derivatives that we need. So we have 2a e to the 2x. We have for our second derivative, what should I write for our second derivative? So when we take the derivative, another copy of 2 will come down front. So we'll have 4a times e to the 2x. We'll go ahead and plug in, and I'll plug in the same way we did before. Actually, let me ask, would you guys like me to plug it in the same way as before? Or did you like the way where after that equals, instead of putting a plug-in, we put the 2 times e to the 2x? Do you guys have a preference, first way or second way? Feel free just to type a number 1 or 2. First way is I'd plug in next. Second way is I'd put it down in equations. All right, it looks like most of you don't care. So I'll go ahead and do the proper way, which is we'll plug in. So we've got our second derivative. We'll plug in our second derivative, which is the 4a e to the 2x. Then we subtract 4 times the original guess. Go back to our original guess. That's this guy right up here at the top. So that's 4 times a e to the 2x. And then, oh no, what happens? What do I get after that equals when I go ahead and simplify or add those together? Yeah, so they're actually going to cancel out and get 0. Now, anybody have an idea of what this means? What does that tell you about your guess for your particular solution? Does that guess work? Does it not work? Ooh, I like the question. It's not a solution. Yeah, so that would actually mean that this guy is not a solution of the non-homogeneous guy. What it does tell you is that it is a solution of the associated homogeneous guy. Okay, so this guess is really a solution of or to the same derivative part, but equal to 0. So if we had done step 1 first, the thing that we've been skipping out on for most of today, we would have actually seen that ahead of time. Okay? So, conclusion, what we want to do here is we want to have a new guess. And our new guess is exactly what a couple of you guys sent me, which is you multiply the old guess by x. So x times a e to the 2x. Please don't really write it like that. You want to reverse the a and the x. Those two really should be reversed. Okay? Then you do the same thing again. So here what you would do is you'd say, hey, I'll find my derivatives. So the guess here now is ax e to the, 2x? Then you've got your first derivative. Now what's different about the first derivative this time with this new guess for a particular solution? Yep, now you have to do a product rule. So if you multiply by an independent variable, you are always going to have a product rule format. So here we'll have, if we take the product rule, a times e to the 2x, so derivative of ax is simply a, plus, well, when you take the derivative of the second part over here, you'll get a copy of 2 come down, so you'll have 2 times ax e to the 2x. Now, here's a trick with exponentials. This is one of the few times that people will recommend this to you. Factor out the e to the 2x. If you factor out the e to the 2x, and if you want, factor out the a as well. So let's go ahead and factor out both the a and the e to the 2x. First term becomes 1. Second term after factoring becomes 2x. Don't forget the x. Now, the reason that I did that is because you're going to have to use product rule to get the second derivative as well. And if you kept it in the non-factored form, that would be just fine, but there would be 3 derivatives you'd have to worry about. The term right here all by itself, and then the product rule on that second term. By factoring out the a times e to the 2x, we only have a product rule, and it actually saves you a third of the work. Again, do not have to do this, but it does save a little bit of work. And if you have a little bit more complicated functions in this, it would save you a lot of work. When I say more complicated, I mean, suppose you had the third, fourth, fifth derivatives you had to compute. This way, it would save you tons of work. So if we take the derivative of this, the first derivative, I'm going to use the factored form. Product rule says take the derivative of the first. Well, the derivative of the stuff inside the parentheses is just 2, so we'll have 2a e to the 2x. And then the next term is we're going to take the stuff in parentheses, and it stays the same. And the derivative of the stuff not in parentheses is going to be, well, you have the extra copy of 2 that comes down. In order to make our life easier in terms of the plugin, I'm going to go ahead and just expand out and combine like terms. Are you guys okay if I do all of that in one step, or do you want to see all the work? I'm seeing no response, so I'll talk us through it. So we're going to have 2a e to the 2x. This 1, when you multiply the 2a e to the 2x through, would be another copy of that. So there would be a grand total of 4a e to the 2x. And then the remaining term, the only thing not underlined, would be when you multiply your 2x times your 2a e to the 2x. So that would be 4ax e to the 2x. Order in multiplication doesn't matter, so if you jumble those characters, that's okay. However, it's proper to go ahead and put the x after the a. And since I did now get a couple of comments in terms of showing work, here would be the middle step. The middle step would be your 2a e to the 2x. The first term would stay the same. The second term, when you distribute the 2a e to the 2x, would be the second copy of 2a e to the 2x, plus multiply this 2x times 2a, and that would give you 4ax e to the 2x. And notice the only things that combined were those 2a e to the 2x's, which is where the 4a in that first term came from. Questions? Make sense? Kind of feeling okay? Notice when you have to multiply by an independent variable, your derivatives start getting a little bit messy, just like when we had trig functions. All right, so in order to have enough room to complete everything with the plugin, I need to go ahead and erase what I just wrote for that middle step. So for the plugin, we've got second derivative minus 4 times your guess. So your second derivative here is 4a e to the 2x plus 4ax e to the 2x. Then we're going to subtract 4 times the original guess. The original guess is ax e to the 2x, which means when you add that all together, what happens? Things will cancel. Specifically, what terms cancel? They're the terms with the blank in them. So depending on how you want to think about it, the final answer after you do all of the arithmetic here is going to be 4a e to the 2x. But in terms of the terms that cancel, all the terms that cancel are the ones with that extra copy of x in it. That's what must happen. If it doesn't happen, it means you did something wrong with the algebra. Why did that have to happen? Because this expression right here must equal the 2e to the 2x. In other words, it can't have that extra copy of x, that extra factor of x out front. Now, once we go ahead and set our simplified expression equal to the non-homogeneous part, could we go ahead and solve for a? And hopefully the answer is yes. What do you guys think? Could we solve for a? Hopefully you're all thinking, yes, I am getting yeses coming in. Awesome. Anybody got what a equals? So a here equals 1/2, which tells you that your particular solution is 1/2 x e to the 2x. And notice the only thing that we changed in the original differential equation was the fact that we had a 2x in the exponent of e instead of a 3x. That one teeny tiny change actually did cause a lot of other changes to happen. Now, here's how you'll know, or how you can recognize that you need that extra copy of x right here for your guess without doing any of the work on that left side of the screen. So I am about to switch to a slightly different application because I didn't leave myself enough room on that screen. So, out of curiosity, can you see both screens right now, the slide and then another screen? Kind of, with one of them sort of covered up. There. Is that useful, or do you want me to just have the new blank one? There, they should now not be covered up. All right, so you guys let me know if you can see what I'm about to write okay or not. If it's too tiny, I'll hide the work we just did. Okay? So using that same example, so example continued. Here's the other way. Remember how we've been skipping out on our step 1? Find the homogeneous solution? Wow, that doesn't say that. Just a second. Okay. Well, if we had actually gone back and looked at our associated homogeneous solution, so we're looking at second derivative minus 4 times the original guy equals 0. There's your associated homogeneous solution. Our characteristic equation is going to be r squared minus 4. Remember, we talked about second derivative turns into r squared. Regular old guy turns into r to the 0, which is 1. If you then factor the r squared minus 4, what are your two factors? Anybody got what the two factors are? So this would be r plus or minus 2, which means what are the two roots? Well, they would be e. No, they wouldn't be e. We're not ready for e's. The two roots would be what? Plus or minus 2. So you have 2 and negative 2, which means our two associated functions would be y1 equals something, y2 equals something, both cases e raised to something. So in y1, we'd have e raised to the 2x corresponding to the root that was equal to 2. And in y2, we would have the exponent of negative 2x. Now look back at our guess for our particular solution. When we then jump into step 2, where we want to find our particular solution, when we go for our initial guess, yp equals, what did we say it was originally, a times e to the 2x, do a quick look, and that is exactly the same as that part. You matched a homogeneous solution, so what that tells you is immediately we say that is a bad guess, so our new guess would then be same as before, but now multiplied by an independent variable. And I can tell you straight up without doing any plug-in whatsoever, that new guess is going to work. Why? Because x times e to the 2x is not a homogeneous solution, excuse me. Okay. Now, it doesn't tell me what A is. I still got to do all of the work that we did on the right side of the other screen to actually solve for A and get the 1/2, but it would tell you that you wouldn't start doing a bunch of derivatives and plug in and get nowhere. You wouldn't get an equal 0. Questions? Make sense? Kind of okay-ish. All right, so I am seeing no new questions from you guys, so I am going to say that let's stop here for today. Next time, then, what we'll do is we'll look at examples where the non-homogeneous part of the differential equation isn't just one of the straightforward polynomial, trig, or exponential cases. What happens if there's some sort of combination of the two?